All right, so we continue with random variables. Let me give the basic definition. Given a sample space S, a function x from S to real numbers is called a random variable. The range of x is denoted by Rx. Okay. Here's an example. A coin is tossed and upper side is observed. So your sample space is heads and tails. Let x be the function xh equals to 1 and xt equals to 0. So I denote tails with 0, heads with 1. So my actual range, in this case, 0 and 1. This is not an interval, just two values, 0 and 1. Another example is that, just choose a random point. So let this be our function x. Randomly choosing a point in the interval 0 between 1 is actually, a random variable with the range 0 between 0 and 1. So in this case, this is an interval, of course. This is just two elements in a set, but this is the interval, so there are infinitely many elements here. So here, as you can see, this is, for this reason, I will call this one a discrete and this one continuous. So let me give the proper definition of random variable types. A random variable is called discrete if the range of x is a discrete set. In other words, a subset of z or q. In this case, as you can see, it is just subset of z, 0 and 1. Or it is continuous if Rx is a union of intervals in real numbers. So it is just, as you can see, an interval. So we divided as discrete and continuous, so because we will talk about discrete distributions and continuous distributions, random variables, in other words. Okay. Equivalent events. If A is an event in the range X, so that, A is a subset of this range, let B be such a set that's consisting of elements S, where XS in this A. We call A and B equivalent events and define P equals to B, because B is always, this A. So let me give an example to explain the equivalent events. Let two dice be rolled. In this case, you are rolling we are rolling two dice, and first result let's denote it with A and the second result with B. So A can be between 1 to 6. Of course, this is not an interval, meaning that 1, 2, 3, 4, 5, and 6. And similarly, B is a 6-sided dice. Of course, if you're a Dungeons and Dragons player, your regular dice would have more sides, like 12 or 20, 20 being the most famous. But in this case, let's stick to the regular die, sorry. All outcomes are equally likely, so they are fair. So probability of observing AB for a specific AB is just 1 over 36 because they are independent events. Observing a value here has probability 1 over 6 and a value here is 1 over 6. So you multiply it and the probability of observing A and B is 1 over 36. So let's define a random variable x so that x be the sum of A plus B. If you think about it, now the range can start with 2, not 1, because the smallest A can get is 1, smallest B can get is 1. So if you add them, you will realize that it will be 2. You can also observe 3, 4, 5, 6 until 12. So of course, some of the values can be observed more than one way. So A being 1 and B being 2 gives you 3. But the other way around is also the same. If A is 2 and B is 1, you would also observe 3. So observing these values have different probabilities. So if we calculate it, if we write the range of x, the summation being 2 has probability 1 over 36, but it being 3 has probability 2 over 36, 3 over 36, and so on. So at 7, we will see the maximum probability, which is 6 over 36, which is 1 over 6, and goes other way until 1 over 36 to observe 12. Okay. So, the probabilities of observing 11 and 3 are identical because their probabilities are the same, right? They're equivalent events. But you have to here, understand something. For instance, if you are playing backgammon, then, for instance, if you want to station your piece to the enemy, it looks like it is better to, stay away from the distance of 7 because there are many ways to roll 7, right? So this actually tries to explain it. Yeah. All right. So here, rolling 1, 2, and 2, 1 is, equivalent events. That is what we try to, give the definition above. Okay. All right, so let's continue with more definitions. Given discrete random variable x, the function px of x, where capital X equals to small x for all x in the range, is called the probability law or the probability function of x. So that this function is always greater than equal to 0, and summation of all of these probabilities give you 1. As an example, let's look at the discrete uniform random variable. A random variable x is called uniform with parameter n if the range is starting from 1 to n and the probability of these x's is constant, so that the summation of them, it gives you 1. But since they are constant and summation gives you 1, this means that this probability should be 1 over n. So this is actually the probability law for uniform discrete uniform random variable or uniform distribution. Okay, so this is one of the basic distributions you can think of. And for these, we define probability density functions and cumulative distribution functions. So let fx be the probability of x not equal to something, but being less than or equal to some value. Okay, we call fxt the cumulative distribution function and px the probability density function. These are the definitions. So now we can talk about summary measures like expected value or variance or standard deviation. Given a random variable x, the expected value or mean of x is denoted by ex, sometimes mu x, and is defined as like this. So if x is a discrete random variable, this expected value is the summation of every x multiplied by the probabilities of those x's. But if it is a continuous random variable, we don't sum values, we actually take the integral from minus infinity to plus infinity. If both the sum and integral are absolutely convergent, of course. The variance is defined with respect to expected value. So variance x is actually expected value of x minus expected value of x squared, which can be evaluated as like this. Okay. And there are some probabilities. For instance, variance of x plus k actually equals to variance of x. And if you multiply with k, k goes outside as square. These are some, formulas or theorems or properties I want to give you without, really calculating them or proving them, just to give you the big picture, and you might need it in the future. Standard deviation is just the, square of the variance. Yes, here's an example so that we can, talk about all of these definitions. So let's look at the discrete uniform random variable. So we defined it as follows. When x is something between 1 to n, so a discrete value, the probability is 1 over n, and it is 0 otherwise. So expected value is, we defined it like this, summation from k beginning from 1 to n. So k take all of these values. And the probability of these values are just 1 over n. So if you calculate it, since, this is a summation with respect to k, so 1 over n is just a constant, we can take it to the front. And if you make this summation, you have to recall that this is just n times n plus 1 divided by 2. So n's cancel each other. So the expected value becomes 1 plus n over 2, which is not surprising, right? So if you instead calculate x square expected value, we write this time k square here, you calculate it, and you end up with this value. So this way, recall that I defined variance by the, using these two values. So, this one minus expected value square of this value. So variance is this. So this way, we calculated the expected value and the variance of discrete uniform random variable. Of course, if you take the square root, then you obtain the standard deviation. All right, so let me give some concrete examples of discrete discrete distributions, random variables, because we want to talk about binomial distribution, which will be helpful for us. So in order to talk about binomial distribution, first we need to talk about Bernoulli distribution. Consider an experiment with two possible outcomes called success and failure, S or F. Let X be the associated random variable where xs equals to 1 and xf equals to 0. Of course, you could define it other way around. And let p1 equals to p and then p0 equals to 1 minus p, which is q. So here we are actually saying that since we're now representing them with 1 and 0, probability of observing 1 is p, probability of observing 0 or failure, has probability 1 minus p, because the summation of these two has to sum to, 1. So p plus q should be 1. So our density function now defined like this, px times q 1 minus x, but x can be either 0 or 1. So, you end up with p or q. Expected value is, 1 times p plus 0 times q equals to p. And variance is just p times q. I'm not, going to calculate all of them, but you can just blame or do it, the exercise by yourself. These are the expected values and variance of Bernoulli distributions. Let's move on to binomial distribution. That's actually interesting to us because we are going to use this in cryptanalysis when we are trying to do, any statistical attack like differential or linear cryptanalysis. What we are going to do is to actually have a lot of input-output pairs and check if they satisfy some property. So that property, satisfying that property, should have a probability like p here. And in the Bernoulli distribution, we were just looking at the success or failure of an event. But when I try to cryptanalyze, I will get a lot of, plain text and ciphertext pairs. I will just check if they satisfy my property. So if they will be failure or success. So I will repeat this Bernoulli trial many times. So consider n independent Bernoulli trials, each with probability of success equals to p and probability of failure equals to 1 minus p, which is q. The sample space of the set of trials S is a set of n tuples t1 to n, where each ti is either success or failure. And the independence of trials gives probability of all ti's, which equals to, if you have m success, then you will have p to the m times q to the m minus m, because there will be m minus m failures, with m, the number of success in the tuple. If the aim is to observe the number of successes in the n trials, then we know that for each m equals to 0 to n, there are nm n tuples containing exactly m successes. So the probability of obtaining m successes, m is less than or equal to n, is, n choose m multiplied by p to the power m times q to the power m minus m. So all of these are coming from the definition. We are just trying to see what happens if we repeat a Bernoulli trial n many times. So this is your probability density function. Your expected value, it is not that hard to calculate, but I'm not going into details, is just n times p. So this means that if your success probability is p, and if you repeat this Bernoulli trials n many times, your expected value is n times p. So this is what actually we expect. So we will find a weakness in the cipher. So observing that weakness will have probability p for the correct key. So if I repeat this, check if any pair satisfies this property with n many pairs, so I will expect n times p many of them to satisfy. So this is why expected value works like this. In the variance, you also get q here. So there are many discrete random variables. We talk about Bernoulli distribution to move on to binomial. So this is very important for us. So this is where I stop actually. But there are other famous discrete random variables like geometric distribution, negative geometric distribution, Poisson distribution, and hypergeometric distribution, where Poisson is actually, very famous, and it is used to explain some of the, events in the nature or so on. So also you might need it in some cryptanalysis results, but this is the thing we need, and this is where we stop. For the continuous random variables, there are many like exponential distribution, Erlang, gamma, normal distribution. So actually I haven't explained any of it, which is because we don't want to go that much amount of detail in probability theory, but normal distribution is very useful to explain a lot of events. Also, sometimes it is hard to calculate the binomial distribution. If you go back, just look at this formula. In our trials in cryptanalysis, we will repeat the experiment n many times. This means that you will repeat this m for n many plain text ciphertext pairs. So maybe our n will be 2 to the 100. Okay, and will also be something large. So this calculation or this summation will be very large. Okay, so instead of calculating it, sometimes we will make an approximation where for some values, you can calculate this, you can approximate these values simply by using normal distribution, which is just calculating an integral. Instead of doing all of the sums, you will simply do a integral calculation and obtain the result. So these are some of the basic concepts I wanted to talk about probability theory, which might be useful when you work in the area of cryptanalysis.